Okay, so we have the rule. B to the A equals C is equivalent to log base B of C equals A. So let's say now we just have a variety of expressions we might want to invert. So let's just say we have 3 to the x equals 5. Okay, well, 3 to the x equals 5, and I'll say this quickly. 3 is B. A is x and C is 5. So the equivalent statement is log base B of C equals A. So we have log, and it's base B, so B is 3. C is 5. And A is x. Well, that's our solution. So x equals log base 3 of 5 is the exact solution of the equation 3 to the x equals 5. You have no other way of getting an exact solution. This is the notation for the exact solution. Now, on your calculator, x equals log base 3 of 5 equals log of 5 divided by log of 3. And your calculator will approximate. Your exact solution. I want to relate this to basic functions. Okay, now 3 to the x isn't one of your basic functions, 2 to the x is. But we can easily make a table for y equals 3 to the x. And you can easily verify that this is negative 1/9. This is negative 1/3, and it's not negative. I understand how students write that down. You got to be careful. And this is 1, and this is 3, and this is 9. So there are my values. We can write the table. We can use the table to construct the graph. So here's 2, here's negative 2, and here's 9. Because 9 is the biggest value you have. Okay, well, we can't subdivide that in 2, but we can subdivide it in 3, more or less equal intervals here. And then we subdivide each of those into 2 subintervals. And we have a reasonable set of y values. Now the y value here is 1, and we're going to have to divide that down into thirds. It's going to be a little hard to read these marks, but you got a couple of small marks here. And then you would have to divide this smallest mark, the interval of this smallest mark, into 3 parts. And I'm not going to even attempt to do that. It's going to be down really close to the axis. So you'd have negative 1 here, we'd have 1 here. So we have a point that's 1/9, which is really small, almost on the axis. And then we have 1/3, which is a little bit above the axis. And we have 1, which is right here. Then we have 2, 3 right here. And then we have 0.29 right here. And here we have a reasonable graph of y equals 3 to the x. It's a whole lot like y equals 2 to the x, but your x-axis is labeled a little differently. Okay, and it rises more steeply, and it approaches the x-axis as an asymptote more quickly, excuse me, than this function. Okay, 3 to the x equals 5. We solve that equation approximately. So here's 1, 2, 3, 4, 5. Here would be our solution. Of 3 to the x equals 5. And it appears to be maybe 1.4. And we'll put a question mark on that. But there's a graphical picture of a solution of this equation, and that's an important picture. We could also make a table for the log 3 graph by simply reversing these columns, because that's how you do an inverse function, and the log base 3 graph, the log base 3 function is inverse to the 3 to the x function. And we can easily graph this now. And the graph is going to have points with the same coordinates as this graph, but the coordinates are going to be reversed. And that's going to give us a graph that is trying to decide where to put my x-axis. The graph that goes out to 9 here, because these points go up to 9 and they go back pretty close to 0. And we have -2 here, 2 here, so 1 and -1 would go here. And we have, well, here we've got 9. Let's subdivide these intervals, and then subdivide these intervals, and then subdivide this interval from 0 to 1. So here's where x equals 1. And here's where x equals 1/3. We get the point 1/3 -1. Well, here's 1/3 and here's -1. That will be about here, pretty close to the y-axis, and similarly to the way our -2 1/9 was very close to the x-axis. 1/9 -2 is going to be very close to the y-axis. So it's going to be kind of hard to distinguish it from the y-axis. Corresponding to the point 0, 1, we'll have the point 1, 0. Corresponding to the point 1, 3, on this graph, we have the point 3, 1. So we come out 2, 3, up to 1. And the point 9, 2 here, corresponding to the point 2, 9 here. And we get a graph that looks like this, and this is a graph of y equals log base 3 of x. So if we want to now solve 3 to the x equals 5, we see that the solution, the exact solution, is going to be log base 3 of 5. X will equal log base 3 of 5 by this rule. But we can see the connection between this rule and these graphs, because log base 3 of 5 means that we come over to 5, 1, 2, 3, 4, 5, and we come up here and over here. Now I notice that this went out a little bit, so this point's a little higher than it ought to be, but my honest estimate from what I just did would be y approximately equal to 1.5. I think 1.4 is a more accurate. I think it might even be like 1.38 or something like that. But you can easily do that on your calculator. The exact solution is log 5 over log 3. And log 5 is 0.31. Log of 3 is about 0.2. Something's wrong with my recollection of what these logs are. In any case, if you plug that into your calculator, you find out what the solution really is. The point of understanding these graphs is, number one, to reinforce what an inverse function is. Number two, give you a graphical picture of what these relationships mean. Number three, to make this whole thing plausible. So, by doing your own graph, making your own estimates, you can verify whether these estimates were any good. And actually, when I do this calculation, I get something closer to 1.6. But that doesn't fit with the concavity of the graph. So, not going to worry about that, but there's a picture. Okay. Now I kind of want to keep this up there. And I didn't get those two small boards erased. And, okay, didn't know what I was looking at. Okay. I'll do a couple more examples a little more quickly. Get this chalk out of the way so I can move this over. Okay, let's say we have now log base 5 of x equals 30. So, well, let's see. B, now if we got log base b of c equals a, then log base 5, log base b is 5. C is what you're taking the log of, that would be x. and A is 30. Thus, b to the a equals c, that's 5 to the 30th, equals x. Okay, well, 5 to the 30th is really a big number. But if we were graphing 5 to the x, it would be even steeper than the graph of 3 to the x. It would go up even faster, and by the time you get out to 30, which is going to be, if 1 is here, 30 is going to be about here, that graph is going to be astronomically high. Matter of fact, it's going to be well beyond the orbit of the moon. Okay? The graph is going to really go up there. But that would be your solution. Okay, well, when you're first doing these, you want to write out these rules. You want to carefully identify A, B, and C. A, B, and C. Once you get used to that, it becomes pretty easy to write these down. But you want to make sure, okay, you want to make sure you're writing them carefully. So let's say we have something a little more complicated, like log base 4 of 7x minus 3 equals 2. Okay, rewriting this is equivalent to saying that 7x minus 3 equals 4 raised to the second power. Now it's fairly easy to keep track of b. You know, b is your base. That will be either here or in exponential form. It'll be the base of your exponential. So if you got a 4 here, you're going to have a 4 here. So if you got a base 4 log, you're going to be doing a power of 4. Well, this is easy to solve. And you can easily solve this. You solve this in your head. Add 3 to 16, you get 19, and then you're going to divide by 7. You get x equals 19/7. Since this was an integer power with an integer base, it was easy to complete the solution. Let's say we have E. To the x squared minus 5x, I'm going to make that minus 6. And let's say that equals any old number, 38. Okay? How do we solve this? Well, this is equivalent to the log base e, because e is the base of your exponential. It'll be log base e. And the expression involving x, the thing you're trying to solve for, comes down here where you can deal with it. Okay, now how are you going to solve this equation? Well, you have to recognize this is a quadratic equation. It follows that Now, I'm sorry, Zoom's acting slowly. Had to pin this. So it follows that well, I can write this like so. It's a quadratic because it's got an x squared and an x, and then -6 is a number. Log base e of 38 is just a number. You don't know what that number is until you approximate it with a calculator. It's going to be kind of close to 4, but a little less. I'd say about 3.7, but you don't need to know that, obviously. Okay? So how do I solve this? Well, let's rewrite that. You got x squared minus 5x minus the quantity 6 plus log base e of 38 equals 0. This is of the form ax squared plus bx plus c, where a is 1, b is -5, and c is 6 plus log base e of 38. Well, I'm going to say, I'm just going to estimate log base e of 38 is about I'm going to guess 3.7. Now I've been writing log base e of 38, but log base e is a natural log. Okay, so I can write this as 6 plus natural log of 38, which of course makes it easy to punch into your calculator. Just natural log of 38. Now it's hopeless to factor this because, of course, this is an approximation to an exact number that goes on forever. No way you're going to factor it. You just have to write out the solution. So x will be approximately equal, and we say approximately because 3.7 is an approximation. In the first place, it's an approximation out of my head, so you have no idea how accurate it is. In the second place, no matter how accurately you approximate this with your calculator, it's still an approximation. It's an irrational number. Just keeps going. Never repeats. Okay? So x is approximately equal to what? Well, you just use the quadratic formula. 5 plus or minus 25 minus 4 times 1 times 3.7, all divided by 2. And that's going to be 5 plus or minus the square root of 4 times 3.7 is 14.8. 25 minus 14.8 is 10.2 over 2. And that's approximately equal to 5 plus or minus 3.2 over 2. And that's like 4.1 or make sure it's 1.8, 0.9. Now, unless I've completely lost my mind, I think it's only partially gone right now. These should be fairly good approximations. They shouldn't be far off of the accurate solution. However, you can check it if you wish. Okay? So you can run into problems of this nature. Okay, now I want to talk a little bit about the intuitive idea of logarithms and how they are important and how they're applied to certain models.